All right, we are kicking off with Unit 1.1, which is focusing on atoms, subatomic particles, isotopes, and the periodic table. Now, the document that I'm looking at here is referred to as blank notes in D2L. These documents can be accessed for each unit that we cover. And as I am speaking, you will follow along and fill in the blanks on these notes here. I would recommend downloading them so you can edit them in Microsoft Word, but another option is to print them off and physically write on them if that's what you're more comfortable with. So what we hope to cover today is the building blocks of life, and this all starts with chemistry. So some of you might be thinking to yourself, this is a biology course, why are we talking about chemistry? And the answer to that is that the smallest building blocks that essentially create life are chemical compounds, molecules, and even smaller atomic elements. And what does chemistry ultimately study? Chemistry studies all of matter. What is matter? So if we start out here with the notes, what we're really saying is that matter is anything that has mass and weight and takes up space. So this could be anything from water to clouds, the breath you expel, you and me. All of these things have mass and weight and take up space. So pretty much anything you can think of is matter. And this is ultimately what chemistry is studying. Matter is the building block of life in a sense. And so what we're really asking here is, what are these building blocks? What are the rules that govern them? And what is their purpose? How do they aid the creation of life? Another concept that is important to think about with matter are the different states. So there's 3 states of matter. Anything that is solid, liquid, or gas. Sometimes thinking of gas as matter is difficult for people, but in the example I just gave with the cloud or the breath you expel, the water vapor in the gaseous form, that is also considered matter. So when we are referring to matter, what is matter really made of? It is made of atoms. So under here, under our notes, we're going to say atoms make up all matter. And this is something you all may have heard in past courses, past chemistry courses, but you can think of an atom as the basic building block of life. So essentially, atoms can form together to create compounds and molecules, and compounds and molecules can then make up small cell structures, all the cells that are in our bodies that could then create organs, organ systems, entire beings. It all starts with this very small subunit that we call the atom. What are the size of atoms? Atoms are extremely small spheres. And they function like Lego pieces. So in a sense, you can think of an atom as a Lego, and as you build with Legos, you can make any different type of variety of configurations, technically an endless number of configurations to create different aspects of life. So I have this document here, and I want to illustrate just how many atoms there are in you, for instance. So let's take, for instance, the number of people on Earth. That's about 7.8 billion people. So we have standard notation, scientific notation 7.7, really indicating 7.8. Times 10 to the 9th power. And if you're not familiar with scientific notation, don't worry, we will cover that in another lecture. But essentially, we start out with 7.8 billion people on Earth, and you might think that's a large number. I can't even fathom 7.8 billion. But it gets quite larger than that when we're talking about the number of atoms. So if we move to the next example here, dollars the Earth is worth. So if you took all the different types of currency, nickels, dimes, dollars, quarters, other types of foreign currencies, and took everything of value on the Earth, you're essentially looking at this incredibly large number here, 3.2 with 14 zeros after it, if we're looking at it in scientific notation. But then it can even get larger if we're talking about grains of sand on the planet. So if you've been on the beach, right, you're familiar with the fact that there's a meticulously large number of grains of sand. And this is to the 18th power. So you're taking 1 and multiplying it by 10 to the 18th power. Again, an incredibly large number. Even larger than that, if we're not talking about grains of sand on the planet, we're talking about stars in the universe. And this is incredibly vast. I can't even fathom a number this large, yet there are still more atoms in you than there are stars in the universe. And not even by a small amount. You'd have to multiply the number of stars in the universe by millions to get the amount of atoms in you. I think that's incredibly fascinating, right? So you have trillions of atoms in you. And if you had to think, how would I even conceptualize a billion atoms? Like, say you have a hangnail or something like that, you have a very small portion of skin on your fingertip. That alone is billions of atoms that you could shed in a single second. So just to give you an idea of how small the atom is and how many there really are when we're talking about people or large complex systems, which is what you are a complex system. So just to recap some notes at the bottom here, everything is made up of atoms. Atoms are nature's building blocks. They can be assembled into an extremely large array of structures. So say, for instance, all the atoms that are in the configuration of a pop can could be rearranged in theory. And if you have the right type of atom, right, you could recreate, say, a person or a book or any endless other array of objects. And it's really just about that configuration of the atoms. And they're so small, it takes an amazingly large number to create anything. So going back to our atoms here, atoms themselves are actually made up of smaller particles. We call these subatomic particles. So there's 3. It's best illustrated in this diagram here. So if you break down, if you're thinking about an atom and you think about it, even like what creates an atom, electrons, protons, and neutrons, and we will start to cover those in the next lecture. So don't worry if you are racking your brain trying to remember what each of these subatomic particles are. So this is the basic structure of an atom. We will get into that later, but I wanted to talk a little bit about elements. So now we're familiar with atoms. We're saying atoms are small spheres and they make up all matter. But what are elements? If you've taken a chemistry class, you've definitely heard of elements before. Essentially, you could take, like, even though there are trillions and trillions of atoms that make up you, there are very common atoms. So if you basically picture all the atoms, they can be sorted into buckets based on their type. And there's approximately 120 different types of atoms. And if you wanted to know what those are, you would look at the periodic table. So for instance, all organic molecules on Earth contain carbon, hydrogen, and oxygen, right? Sugars, any type of common structure, contain just 3 different types of atoms. So we have some that are incredibly common, hydrogen, helium, right? All different types. However, there are also lesser known atoms that you might only work with, say, if you are a chemist. And as we go further and further down the periodic table, and these increase in mass, that's how the periodic table works essentially, is the further you move down the rows, the greater mass that the atom contains. You might have some very niche atoms that are only worked with in specific projects or for specific purposes. But for the most part, there's a very small number of buckets that all the atoms of our everyday life fall into. And those are probably closer to the top of the periodic table. And one thing to note about elements, so an element is a type of atom. It cannot be broken down further in a chemical reaction or by a chemical reaction. And we can talk more about what a chemical reaction is in a later lecture, perhaps, but really the idea I want you to take home is just that elements are the building block. It is a type of atom. There are very few common types of atoms that make up the majority of compounds that we work with on Earth. They are listed on the periodic table, which we just displayed. And each element has unique properties and behaviors. So different atoms may be used for different purposes depending on the type of space they need to fill and the types of properties that are needed by whatever it is building. So a good example here is atomic weight. So on each of these elements on the periodic table, there's some information that is summarized up here at the top. Atomic weight is one of those characteristics that may impact where atoms are used best. Another is, if we're looking back at this diagram here, the number of electrons and the number of electrons here essentially, if you lose those electrons, it makes certain types of atoms more attracted to one another. They have a higher affinity for one another. And so basically each atom, when it loses or gains electrons, has unique properties that allow it to bond to other things. So that's just one other aspect to keep in mind about elements. One other important idea to take away about atoms, and similarly with elements, is that atoms are not in themselves alive. So if you had a pair of atomic tweezers and you took apart a person atom by atom, you would essentially have, let's say the average person weighs 150 pounds. You could have 150 pounds of atomic dust of these tiny spheres, and not a single one of them would be alive. And that is one of the most interesting aspects of this chapter that we're covering, is that it's really when they start to form other structures and start to differentiate into cells and other types of actual living subunits, is that we really see life form. But atoms in themselves are not alive. And that's one important thing to take away here. All right, so that's an overview of a basic subunit. So what happens when we start to combine atoms or combine elements? We essentially start with compounds. So a compound is a substance with two or more atoms. So they have to be different atoms. So if you have two different types of elements chemically bonded together, that would be a compound. However, if they are two of the same element bonded together, those would not be a compound. And the difference here, right, because we're starting to, like, say you have a blue Lego and a red Lego, and you put those together. Now you have something that can be broken down into more, basically smaller, more simpler structures, right? So the difference between a compound and an element is a compound can be broken down and remade. And that's what makes this Lego analogy so great, is that if you're playing with Legos, right, you can put them together, take them apart. It's the same exact thing when we're talking about building compounds with elements. So an example of a compound could be water, for instance. So water would be H2O. And I'll just use the chemically correct subscript here, and we'll talk about that in a later lecture. But essentially here, we have two different types of elements. We have hydrogen and oxygen. And here we have two hydrogen atoms bound to an oxygen atom. And that can be broken down further by chemical processes into hydrogen and oxygen. So that is an overview, and there's several different types of compounds that we'll talk about later in this class, but starting out with water is a good example just because we're all familiar with it. But that is an overview of atoms, subatomic particles. In our next lecture recording, we will talk about isotopes and further about the periodic table.